Okay, let's continue here with chapter 13. So still talking about colligative properties. Now let's talk about the boiling point elevation. So since vapor pressure are lowered for solutions, it requires a higher temperature to reach atmospheric pressure. So hence boiling point is raised. So we have the boiling point for the pure solvent, and if you add the solute, you have a higher boiling point for the new mixture, for the solution. So this, and there is these formulas here show how can you calculate, how you can predict it, what will be the new boiling point, the new freezing point. So boiling point elevation and freezing point depression. The change in temperature is directly proportional to molality using the Van Hoff factor. So the Van Hoff factor is this I here. That is the number of particles a substance becomes when it dissolves. So for delta TB, that's the boiling point elevation here. It is delta, the boiling point for the solution minus boiling point for the pure solvent equal to I, the boiling point constant. So each solvent will have its constant, its boiling point constant, times molality. This M here is for molality. And for the freezing point depression, it will be the freezing point, so the solution for the freezing point of the solution minus freezing point for the solvent equal to minus IKF M. And for molality, KF is for the freezing point constant, and the I for the Van Hoff factor. So you have here this table. Let me show here. Molar boiling point elevation and freezing point depression constants. So have here solvent, you have water, benzene, ethanol, carbon tetrachloride, chloroform. You have here this column is for the boiling points, the normal boiling points in degrees Celsius for each of these solvents. The KB is the boiling point elevation constant, and the KF is for the boiling point, freezing point depression constants. So problem 2. A solution of an unknown, non-volatile, non-electrolyte was prepared by dissolving 0.50 grams of the substance in 40.0 grams of carbon tetrachloride. The boiling point of the resulting solution was 0.357 degrees Celsius higher than that of the pure solvent. So the question is asking to calculate the molar mass of the solute. Let's do here. So this they're going to be using this formula here. So delta TB equal to I KB times molality. Delta TB is the molar boiling point elevation, and it's given here, right? 0.357 degrees Celsius higher. So let's plug it here. 0.357 degrees Celsius higher. The I is the numbers of particles, right? Is the about the Van Hoff factor. So if you have no electrolytes, you're gonna be using I equal to 1, assuming I equal to 1, because when you have when no electrolytes dissolve, they becomes like one, it's still gonna be one particle. So that's why here I equal to 1 for no electrolytes. So I equal to 1. Kb is the molar point, is the constant for the solvent. In the question here, the solvent, it is carbon tetrachloride, right? So let's use it here. Carbon tetrachloride, the Kb, it is 5.02 times molality. In other words, you had basically everything with exception for the molality. So let's rearrange it here, right? So it will be 0.357 degrees Celsius divided by 1 times 5.02. The unit here is Celsius per mole equal to molality. So we cancel unit with unit here. You do this division here. Your molality will be equal to what? So molar, let's do the calculation. So 0.357 divided by 5.02, it is equal to 0.071116 molality. So I am not worrying for significant figures yet, just in the end of the question, right? So let's go to the calculate the molar mass of the solute. So to calculate the molar mass of the solute, we need to go to use the molality formula. So molality, it is moles of the solute, right? Divided by the kilograms of the solvent. That's right. So what's the kilograms of the solvent here? The solvent was given 40 grams, 40.0 grams. So let's divide by 1,000. That would be equal to, so molality, let's already plug the molality here. Molality is equal to 0.071116 molality, molal, times the kilograms of solvent. That would be 40 grams divided by 1,000. It will be equal to 0.040 grams. Oh, sorry, kilograms, right? That's need to convert from grams to kilograms. So it will be 0.0400 kilograms equal to moles of this solute. So it will be equal to times 0.040 So moles of the solute be equal to, here, right, 2.8446 times 10 to the minus 3 moles of the solute. The question is asked for the molar mass of the solute. No, now to calculate the molar mass of the solute, you already have the moles, and the question gave it to us the grams, right? So how calculate moles number? So, oops, sorry guys. Moles is equal mass over molar mass, right? Then the mass was given. We have more numbers, right? Let's rearrange here. It will be equal, right? When they rearrange here, be equal mass divided by moles numbers. So it will be 0.250, right? This one divided by 2.8446 times 10 to the minus 3. So what going to be the answer here? Divided by 2.8446 exponential to minus 3. So it's going to be around to 80. It will be. So it will be about this number here. It will be this one. 88 grams per mole. Okay? So this question here, we start with this one. First step. Start here. First step, right? Then after did you use the formula for the freezing, the boiling point elevation, you find the molality. After you find the molality, here is the molality. You use it now, the second step, to find the moles of the solute using molality and the kilograms of solvent. After you find the moles of the solute, rearrange it to find the molar mass here. So yes, you have 3 steps here. Okay. Now let's go to osmosis. So some substances, they form semi-permeable membranes, allowing some particles, so allow some smaller particles to pass through, but blocking larger particles. So you'll be passing smaller particles, but blocking larger particles. And the net movement of solvent molecules from solution of low concentration to higher concentration across a semi-permeable membrane. I have here a semi-permeable membrane here. This process is called osmosis. And the applied pressure to stop it is called osmotic pressure. So let's see here. Look at the volume here. Initially, you have this volume in this U tube here, right? In the middle here, you have the membrane, semi-permeable membrane. So the volume of the pure solvent and the volume of the solution were in the level here, the semi-level, right? And then you can see here the particles of water will go passing the membrana. So we're going to start passing to the solution side. So that means the water volume is decreasing and the solution volume is increasing. So at equilibrium, the flow of water is the same in both directions. That means the volume that is decreasing here. So, right, that means for the volume that increased here. So there is no net movement here at equilibrium. So then to equalize here these levels, we apply a pressure. And this pressure is called osmotic pressure. Are you seeing here that now the level will apply the pressure here, right? Are you seeing this picture? This pressure was applied, so that means this level of this fluid level decrease here, and you have the water came back here. So the pressure applied to equalize the fluid levels in both arms equals to osmotic pressure. So this symbol here is the osmotic pressure symbol, right? That's this one here. And osmotic pressure is a colligative property. If